Radio navigation. A radio navigation is the application of radio frequencies to determine a position of an object on the Earth. Like radiolocation, it is a type of radio determination. The basic principles are measurements from to electric beacons, especially directions, e.g. by bearing, radio phases or interferometry. Distances, e.g., ranging by measurement of travel times. Partly also velocity, e.g., by means of radio Doppler shift. Bearing measurement systems. These systems used some form of directional radio antenna to determine the location of a broadcast station on the ground. Conventional navigation techniques are then used to take a radio fix. These were introduced prior to World War I, and remain in use today. Radio direction finding. The first system of radio navigation was the radio direction finder, or RDF. By tuning in a radio station and then using a directional antenna, one could determine the direction to the broadcasting antenna. A second measurement using another station was then taken. Using triangulation, the two directions can be plotted on a map where their intersection reveals the location of the navigator. Commercial AM radio stations can be used for this task due to the long range and high power, but strings of low-power radio beacons were also set up specifically for this task, especially near airports and harbors. Early RDF systems normally used a loop antenna, a small loop of metal wire that is mounted so it can be rotated around a vertical axis. At most angles the loop has a fairly flat reception pattern, but when it is aligned perpendicular to the station, the signal received on one side of the loop cancels the signal in the other, producing a sharp drop in reception known as the null. By rotating the loop and looking for the angle of the null, the relative bearing of the station can be determined. Loop antennas can be seen on most pre-1950s aircraft and ships. Reverse RDF. The main problem with RDF is that it required a special antenna on the vehicle, which may not be easy to mount on smaller vehicles as single-crew aircraft. A smaller problem is that the accuracy of the system is based to a degree on the size of the antenna, but larger antennas would likewise make the installation more difficult. During the era between World War I and World War II, a number of systems were introduced that placed the rotating antenna on the ground. As the antenna rotated through a fixed position, typically due north, the antenna was keyed with the Morse code signal of the station's identification letters so the receiver could ensure they were listening to the right station. Then they waited for the signal to either peak or disappear as the antenna briefly pointed in the direction. By timing the delay between the Morse signal and the peak null, then dividing by the known rotational rate of the station, the bearing of the station could be calculated. The first such system was the German Telefunkenkompass sender, which began operations in 1907 and was used operationally by the Zeppelin fleet until 1918. An improved version was introduced by the UK as the Orfordness began in 1929 and used until the mid-1930s. A number of improved versions followed, replacing the mechanical motion of the antennas with phasing techniques that produced the same output pattern with no moving parts. One of the longest-lasting examples was SON, which went into operation just before World War II and used operationally under the name console until 1991. The modern Vorsh system is based on the same principles. ADF and NDB. A great advance in the RDF technique was introduced in the form of phase comparisons of a signal as measured on two or more small antennas, or a single highly directional solenoid. These receivers were dramatically smaller, more accurate, and simpler to operate. Combined with the introduction of the transistor and integrated circuit, RDF systems were so reduced in size and complexity that they once again became quite common during the 1960s, and were known by the new name, Automatic Direction Finder, or ADF. This also led to a revival in the operation of simple radio beacons for use with these RDF systems, now referred to as non-directional beacons, as the LF-MF signals used by NDBs can follow the curvature of Earth. NDB has a much greater range than VOR, which travels only in line of sight. NDB can be categorized as long-range or short-range depending on the power. The frequency band allotted to non-directional beacons is 190 to 1750 kHz, but the same system can be used with any common AM-band commercial station. VOR VHF omnidirectional range, or VOR, is an implementation of the reverse RDF system, but one that is more accurate and able to be completely automated. Instead of a single signal, the VOR transmitter sends out 3 signals. One is a simple voice channel that sends Morse code to identify the station. Another is a continuous signal sent in all directions, and the last is a signal that is rotated at 30 RPM. Like the awkwardness concept, the bearing of the station is measured by finding the rotating signal's peak and null. But instead of timing the signal, the rotating signal is changed in phase in synchronicity with its rotation, such that it is in phase when pointed north, 90 degrees off when it points east, and so forth. By comparing the phase of the received signal with the one being broadcast omnidirectionally, the angle can be determined using simple electronics. This angle is then displayed in the cockpit of the aircraft, and can be used to take a fix just like the earlier RDF systems, although it is easier to use, as VOR required 2 VHF receivers as well as a conventional radio for station identification. The system did not become popular until the era of miniaturized electronics, first with small tubes in the 1950s, and then transistorized systems in the 1960s. During this period it quickly took over from the older radio range system. The signals from the stations could be received anywhere, as opposed to the beams which were only broadcast in certain directions. So in theory the VOR system could be used for free navigation from any to any point. In practice, the older radio range procedures were so widely used and standardized that VOR was used to produce a similar set of airways that remain in use today. The U.S. military also introduced a VOR-like system known as TACAN. It differed from VOR primarily in its modulation system, adding a Lor ANC-like signal to accurately define the center of the rotating beam and thereby improve accuracy. It requires 5 receiver channels and additional electronics, an expensive requirement when it was introduced. Beam systems. Beam systems broadcast narrow signals in the sky, and navigation is accomplished by keeping the aircraft centered in the beam. A number of stations are used to create an airway, with the navigator tuning in different stations along the direction of travel. These systems were common in the era when electronics were large and expensive. As they placed minimum requirements on the receivers, they were simply voice radio sets tuned to the selected frequencies. However, they did not provide navigation outside of the beams, and were thus less flexible in use. The rapid miniaturization of electronics during and after World War II made systems like VOR practical, and most beam systems rapidly disappeared. Lor ANC in the post-World War I era. The Lor ANC Company of Germany developed a means of projecting 2 narrow radio signals with a slight overlap in the center. By broadcasting different audio signals in the 2 beams, the receiver could position themselves very accurately accurately down the center line by listening to the signal in the headphones. The system was accurate to less than a degree in some forms. Originally known as Ultrakurzwelle und Landfunkfeuer, or simply Leitstrahl, little money was available to develop a network of stations. Deployment was instead led by the U.S., where it formed the basis of a wide-area navigation system through the 1930s and 40s. Development was restarted in Germany in the 1930s as a short-range system deployed at airports as a blind landing aid. Although there was some interest in deploying a medium-range system like the US LFF, deployment had not yet started when the beam system was combined with the awkwardness timing concepts to produce the highly accurate SON system. In all of these roles, the system was generically known simply as a Lorentz beam. In the immediate pre-World War II era, the same concept was also developed as a blind bombing system. This used very large antennas to provide the required accuracy at long distances, and very powerful transmitters. Two such beams were used crossing over the target to triangulate it. Bombers would enter one of the beams and use it for guidance until they heard the second one in a second radio receiver, using that signal to time the dropping of the bombs. The system was highly accurate, and the Battle of the Beams broke out when United Kingdom intelligence services attempted, and then succeeded, in rendering the system useless through electronic warfare. SON, however, proved just as useful to the UK as Germany, and was left to operate unhindered throughout the war. Low-frequency radio range. The low-frequency radio range was the main navigation system used by aircraft for instrument flying in the 1930s and 1940s in the US and other countries, until the advent of the VOR in the late 1940s. It was used for both en route navigation as well as instrument approaches. The ground stations consisted of a set of 4 antennas that projected Lorentz beams in 4 cardinal directions. One of the beams was keyed with the Morse code signal A.D.A, with the second beam N.D. flying down the centerline produced a steady tone. The beams were pointed to the next station to produce a set of airways, allowing an aircraft to travel from airport to airport by following a selected set of stations. Effective course accuracy was about 3 degrees, which near the station provided sufficient safety margins for instrument approaches down to low minimums. At its peak deployment, there were nearly 400 LFR stations in the U.S. glide path and the localizer of ILS. The remaining widely used beam systems are glide path and the localizer of the instrument landing system. ILS uses a localizer to provide horizontal position, distance to the runway, and airport information, and glide path to provide vertical positioning. ILS can provide enough accuracy and redundancy to allow automated landings. For more information, see also transponder systems. Positions can be determined with any 2 measures of angle or distance. The introduction of radar in the 1930s provided a way to directly determine the distance to an object even at long distances. Navigation systems based on these concepts soon appeared, and remained in widespread use until recently. Today they are used primarily for aviation, although GPS has largely supplanted this role. Radar and transponders. Early radar systems, like the UK's chain home, consisted of large transmitters and separate receivers. The transmitter periodically sends out a short pulse of a powerful radio signal, which is sent into space through broadcast antennas. When the signal reflects off a target, some of that signal is reflected back in the direction of the station where it is received. The received signal is a tiny fraction of the broadcast power, and has to be powerfully amplified in order to be used. The same signals are also sent over local electrical wiring to the operator's station, which is equipped with an oscilloscope. Electronics attached to the oscilloscope provides a signal that increases in voltage over a short period of time, a few microseconds. When sent to the X input of the oscilloscope, this causes a horizontal line to be displayed on the scope. This sweep is triggered by a signal tapped off the broadcaster, so the sweep begins when the pulse is sent. Amplified signals from the receiver are then sent to the Y input, where any received reflection causes the beam to move upward on the display. This causes a series of blips to appear along the horizontal axis, indicating reflected signals. By measuring the distance from the start of the sweep to the blip, which corresponds to the time between broadcast and reception, the distance to the object can be determined. Soon after the introduction of radar, the radio transponder appeared. Transponders are a combination of receiver and transmitter whose operation is automated upon reception of a particular signal, normally a pulse on a particular frequency. The transponder sends out a pulse in response, typically delayed by some very short time. Transponders were initially used as the basis for early IFF systems. Aircraft with the proper transponder would appear on the display as part of the normal radar operation, but then the signal from the transponder would cause a second blip to appear a short time later. Single blips were enemies, double blips friendly. Transponder-based distance navigation systems have a significant advantage in terms of positional accuracy. Any radio signal spreads out over distance, forming the fan-like beams of the Lor signal. For instance, as the distance between the broadcaster and receiver grows, the area covered by the fan increases, decreasing the accuracy of location within it. In comparison, transponder-based systems measure the timing between two signals, and the accuracy of that measure is largely a function of the equipment and nothing else. This allows these systems to remain accurate over very long range. The latest transponder systems can also provide position information, possibly derived from GNSS, allowing for even more precise positioning of targets. Bombing systems. The first distance-based navigation system was the German e.g.by blind bombing system. This used a Lor beam for horizontal positioning, and a transponder for ranging. A ground-based system periodically sent out pulses which the airborne transponder returned. By measuring the total round-trip time on a radar's oscilloscope, the aircraft's range could be accurately determined even at very long ranges. An operator then relayed this information to the bomber crew over voice channels, and indicated when to drop the bombs. The British introduced similar systems, notably the e.g.by system. This used two stations in England that operated on different frequencies and allowed the aircraft to be triangulated in space. To ease pilot workload, only one of these was used for navigation. Prior to the mission, a circle was drawn over the target from one of the stations, and the aircraft was directed to fly along this circle on instructions from the ground operator. The second station was used, as in e.g.by, to time the bomb drop. Unlike e.g.by, e.g.by was deliberately built to offer very high accuracy, as good as 35 meters, much better than even the best optical bomb sights. One problem with e.g.by was that it allowed only one aircraft to be guided at a time. This was addressed in the later GH system by placing the transponder on the ground and broadcaster in the aircraft. The signals were then examined on existing G display units in the aircraft. GH did not offer the accuracy of e.g.by, but could be used by as many as 90 aircraft at once. This basic concept has formed the basis of most distance measuring navigation systems to this day. Beacons. The key to the transponder concept is that it can be used with existing radar systems. The ASV radar, introduced by RAF Coastal Command, was designed to track down submarines and ships by displaying the signal from two antennas side by side and allowing the operator to compare the relative strength Adding a ground-based transponder immediately turned the same display into a system able to guide the aircraft towards a transponder, or beacon in this role, with high accuracy. The British put this concept to use in the Rebecca-Eureka system, where battery-powered Eureka transponders were triggered by airborne Rebecca radios and then displayed on ASVMK. 2 radar sets. Eurekas were provided to French resistance fighters, who used them to call in supply drops with high accuracy. The US quickly adopted the system for paratroop operations, dropping the Eureka with Pathfinder forces or partisans, and then homing in on those signals to mark the drop zones. The beacon system was widely used in the post-war era for blind bombing systems. Of particular note were systems used by the U.S. Marines that allowed the signal to be delayed in such a way to offset the drop point. These systems allowed the troops at the front line to direct the aircraft to points in front of them, directing fire on the enemy. Beacons were widely used for temporary and mobile navigation as well, as the transponder systems were generally small and low-powered, able to be man-portable or mounted on a jeep. DME in the post-war era, a general navigation system using transponder-based systems was deployed as the distance-measuring equipment system. DME was identical to GH in concept, but used new electronics to automatically measure the time delay and display it as a number, rather than having the operator time the signals manually on an oscilloscope. This led to the possibility that DME interrogation pulses from different aircraft might be confused, but this was solved by having each aircraft send out a different series of pulses which the ground-based transponder repeated back. DME is almost always used in conjunction with VOR, and is normally co-located at a VOR station. This combination allows a single VOR-DME station to provide both angle and distance, and thereby provide a single station fix. DME is also used as the distance measuring basis from the military TACAN system, and DME signals can be used by civilian receivers. Hyperbolic systems. Hyperbolic navigation systems are a modified form of transponder systems which eliminate the need for an airborne transponder. The name refers to the fact that they do not produce a single distance or angle, but instead indicate a location along any number of hyperbolic lines in space. Two such measurements produces a fix, as these systems are almost always used with a specific navigational chart with the hyperbolic lines plotted on it, that generally reveal the receiver's location directly, eliminating the need for manual triangulation. As these charts were digitized, they became the first true location indication navigational systems, outputting the location of the receiver as latitude and longitude. Hyperbolic systems were introduced during World War II and remained the main long-range advanced navigation systems until GPS replaced them in the 1990s. The first hyperbolic system to be developed was the British G system, developed during World War II. G used a series of transmitters sending out precisely timed signals, with the signals leaving the stations at fixed delays. An aircraft using G RAF bomber commands heavy bombers examined the time of arrival on an oscilloscope at the navigator's station. If the signal from two stations arrived at the same time, the aircraft must be an equal distance from both transmitters, allowing the navigator to determine a line of position on his chart of all the positions at the distance from both stations. More typically, the signal from one station would be received earlier than the other. The difference in timing between the two signals would reveal them to be along a curve of possible locations. By making similar measurements with other stations, additional lines of position can be produced, leading to a fix. G was accurate to about 165 yards at short ranges, and up to a mile at longer ranges over Germany. G remained in use long after World War II, and equipped RAF aircraft as late as the 1960s. LORAN, with G entering operation in 1942. Similar U.S. efforts were seen to be superfluous. They turned the development efforts towards a much longer range system based on the same principles, using much lower frequencies that allowed coverage across the Atlantic Ocean. The result was LORAN, for long-range aid to navigation. The downside to the long wavelength approach was that accuracy was greatly reduced compared to the high-frequency G. LORAN was widely used during convoy operations in the late war period. Decca, another British system from the same era, was Decca Navigator. This differed from G primarily in that the signals were not pulses delayed in time, but continuous signals delayed in phase. By comparing the phase of the two signals, the time difference information as G was returned. However, this was far easier to display. The system could output the phase angle to a pointer on a dial, removing any need for visual interpretation. The circuitry for driving this display was quite small. Decca systems normally used 3 such displays, allowing quick and accurate reading of multiple fixes. Decca found its greatest use post-war on ships, and remained in use into the 1990s. LORANC almost immediately after the introduction of LORAN in 1952, work started on a greatly improved version. LORANC combined the techniques of pulse timing in G with the phase comparison of Decca. The resulting system radio spectrum from 90 to 110 kHz that was both long-ranged and accurate. To do this, LORANC sent a pulsed signal, but modulated the pulses with an AM signal within it. Gross positioning was determined using the same methods as G, locating the receiver within a wide area. Finer accuracy was then provided by measuring the phase difference of the signals, overlaying that second measure on the first. By 1962, high-power LORANC was in place in at least 15 countries. LORANC was fairly complex to use, requiring a room of equipment to pull out the different signals. However, with the introduction of integrated circuits, this was quickly reduced further and further. By the late 1970s, LORANC units were the size of a stereo amplifier and were commonly found on almost all commercial ships as well as some larger aircraft. By the 1980s, this had been further reduced to the size of a conventional radio, and it became common even on pleasure boats and personal aircraft. It was the most popular navigation system in use through the 1980s and 90s, and its popularity led to many older systems being shut down, like G and Decca. However, like the beam systems before it, civilian use of LORANC was short-lived when GPS technology drove it from the market. Other hyperbolic systems. Similar hyperbolic systems included the U.S. Global Wide VLF Omega navigation system, and the similar Alpha deployed by the USSR. These systems determine pulse timing not by comparison of two signals, but by comparison of a single signal with a local atomic clock. The expensive to maintain Omega system was shut down in 1997 as the U.S. military migrated to using GPS. Alpha is still in use.